We're going to do a problem that involves our alternating series test. The alternating series test states that if we have some series that alternates, that just means that we have -1 to the nth power or -1 to the n-1th power of some b sub n. And we have these conditions where b sub n, the non-negative part, is greater than 0. The b sub n plus 1 is smaller or equal to b sub n for all n. And the limit as n approaches infinity of b sub n is equal to 0. Then the series is convergent. And it's important to note that when we have an alternating series, the first term can be negative or positive. It doesn't affect the outcome of the alternating series test. So we're given a series here, and we're asked, does it converge or diverge? We're not asked to evaluate it. We just want to know if it shoots off to infinity or if it converges to some finite value. And the first thing to notice is that we have cosine of pi times some integer here, n. And that might seem a little bit confusing at first for some. So let's just review exactly what that means. I'm just going to draw a little chart here. Let's say that this is our x-axis and here's our y-axis. Here's going to be our origin. Right about there, that can be 1. This can be -1. And somewhere out here we're going to have pi over 2. And we're going to have intervals of pi starting at pi, or 1 pi. And over here we're going to have 3 pi halves. 3 pi halves. And somewhere over here we might have 2 pi. There we go. So we know that our cosine function is just going to oscillate here, starting at 1. It's going to oscillate between 1 and -1 on intervals of pi. So it's going to oscillate like that, come down here and curve back up the other way, and get ready to go down again there. So in other words, whenever we have odd intervals of pi, like 1 pi and 3 pi and so on, well then we know that our cosine is of pi n is going to equal -1. When we have even intervals of pi, like 2 pi or even 0 pi, we could argue that 0 is an even number, then we know that the output is going to just equal 1. So lucky for us here, notice what happens. We have n starts at 0, so we know that that's going to be 1. So this is the same. This is the same as if we were to say from n equals 0 to infinity of -1 to the nth power. When n is equal to 1, then we're just going to get -1. So here, when n is equal to 1, we're also going to get -1, and so on. These are equivalent statements. 3 plus n. Alright, so now we can go back to our definition here of an alternating series. We see that we do in fact have an alternating series. It's just every other term is going to be positive or negative. And we can pinpoint our b sub n part of our expression here. We know that our b sub n, I'll just write it down here, our b sub n is going to equal this part here, the part that's positive. 1 over 3 plus n. And we know that it's always positive. It's always positive. It is decreasing. as, if you just imagine, if we have for every n plus 1 here, well, that would be 4 plus n is going to be smaller than, or sorry, 1 over 4 plus n is definitely going to be smaller than 1 over 3 plus n. I'll just write that out. We know that this is decreasing because of this. 1 over 3 plus n plus 1 is smaller than 1 over 3 plus n. And you just imagine here, we add 1 to 3, that gives us 4 plus n. We're claiming that that's smaller than 1 over 3 plus n, because our denominator went up. So every time our denominator goes up, well, then our whole expression, the whole value of this expression is gonna go down, and vice versa. So we know that our b sub n here is decreasing, and we can also show that the limit as n approaches infinity of b sub n is going to go to 0. So that's also one of the stipulations of our alternating series test. So just by virtue of these three things being true, we know that our series is going to be convergent. However, we don't know if it is conditionally convergent or absolutely convergent necessarily. So let's just see whether or not, if we get rid of this negative term here, if it's still going to be convergent. Let's say that we have another series here, and let's just take the series of our b sub n from n equals 0 to infinity. Now this is not the same series that we started with here. We're just testing this on its own for convergence. Well, we can do our limit comparison test, and we know that the series of 1 over n is divergent. This is our harmonic series. This is divergent. So we can do our limit comparison test and compare this series with our harmonic series. So let's go ahead and do that. We're going to do our limit comparison test. So limit comparison test. This is our harmonic series here, which is divergent. That's what we're going to be comparing it to. And we're going to take the limit as n approaches infinity of, let's let 1 over 3 plus n be our a sub n here. So I like to write fractions in the numerator. Some people flip the expressions and multiply, but I find it's how my brain works. The limit as n approaches infinity of this, our b sub n, over this a sub n of our harmonic series here. Well, as n approaches infinity, this 3 is going to just become increasingly insignificant, and this whole thing is just going to go to 1. And by the definition of our limit comparison test, some people refer it as LCT for limit comparison test, we know that because this value here is just greater than 0, then both series and our denominator here diverges, is part of a divergent series, then both of these series will diverge. So both diverge. So both of these A sub n and B sub n that are representative of these series here, these respective series here, both of the series will diverge. So therefore, we've just shown that our series that we started with here, n equals 0 to infinity, of cosine pi times some integer, all of that over 3 plus n. It converges. We showed that it converges via the alternating series test, but it only converges conditionally. It converges conditionally via the alternating series test. And I think it's important to point out that it only converges conditionally. Notice we could have just stopped up here. We could have said, oh well, we have an alternating series that passes the alternating series test and therefore is convergent. But without this negative part up here in our expression, it would be divergent. Because when we did our limits comparison test with the harmonic series, we showed that it would have been divergent if it weren't for that oscillating negative part here. So I think that's especially important, and that'll definitely earn you some brownie points if you mention that on your exam.